Alright everybody, welcome to lesson 3 here. This one we're going to talk about our third form that we could potentially see a quadratic equation in, called vertex form. So we saw two other ones in our previous videos. The first one looks very familiar to those ones we factored previously in Math 10, that ax squared plus bx plus c format. And the other one we saw in our last video when we started to solve some of these by factoring. And we said, well, if it's broken up into that factored form, you know, one factor multiplied by another in the set of brackets, well, that told us something about the graph as well, and it really told us where the x-intercepts were going to be. Now, there's a third form that we could use to do all of this same information as well, which is called vertex form. And right here you can see what it looks like highlighted in red. And you know what it really does tell us, it tells us the coordinates of that maximum or minimum point. So here my vertex is given by those two letters, h and k. Now the difficult part about this equation is that in that set of brackets where it says x minus h, it looks like there's a minus sign in there, which really there is, I can see it. But that means that my actual coordinate of my vertex, it's actually a positive number. Okay, not a negative like it would seem, which is very counterintuitive. So we'll graph a few things out, like we did to start some of the other ones, and we'll explain how it changes, what affects it, and what happens to the graph here. So we're going to compare all of these to our original one of x squared. So I'm going to put that into y number 1. So there's x squared. And in y number 2, I'm going to put the other equation. And we saw in the previous video that if I go all the way left and hit enter, I could get a bolded line, which is really going to show me the difference here. So in this one, I'll put in that equation for a. So x minus 3 squared. And then we're going to graph those two things, and we're going to compare them. Okay, so in black, you can really see your original, just, regular old x squared that looks something like this. That should be there. There's my vertex. So here's the original graph of y is equal to x squared. And what you'll see is the new one has basically the same shape, except it's a couple units to the right. Right, every point kind of went right a little bit. Sorry, I'm just sketching this out here, so there we go. Right, the shape of it didn't really change. It still opens the same direction. It really just slided over a little bit. And what you'll notice is my vertex is now in a new place. The original one was on the origin, but now the new vertex is 3 units to the right, and I can see a 3 represented in that set of brackets. So now I know that my x coordinate of my vertex is on 3. Well, there's no y coordinate of my vertex because it really is also acting like an x-intercept. So I know that the number I can add to the back of this is, well, just 0. And, I didn't change the value of anything in that equation because I can add 0 freely. So I know my vertex right now is at a coordinate point of 3, 0, which is what those two numbers tell me anyways. So we could try this for b as well, and we'll change out our y2 equation here, and we'll make it x squared minus 5 instead, and then we'll hit graph. And again, you'll see the same sort of graph. Oh, I didn't bold that one. Let me bold the other one here. Bold, enter. You'll see basically the same sort of shape for the original one, but the new one now has, kind of dropped beneath that x-axis. Right? It's basically gotten lower, and what you'll notice is, well, the original vertex had a y value of 0, but we always said before that the constant told you your y-intercept of your graph, and which is true here because of the format that it's in. So I know my vertex is going to have a y value of minus 5, but I also know the x-coordinate of it is 0, because I could rewrite this as, well, x minus 0 squared, because x minus 0 is just x. Squaring it makes no difference, and then my minus 5 can be on the end. So I know the coordinates of my vertex here are 0, -5. And again, it's those same numbers from that equation that are going to tell me where that vertex happens to be. And you'll notice that each of the time there's a subtraction in it. So for the first one, I knew it was a positive 3 because my graph went 3 to the right, even though it said minus. The sign is a little bit backwards here. Okay, but let's try one where maybe there's a plus sign instead. So I'll graph you the original one again. It'll look something like this. Not perfect, but it'll get the idea across. And this one will change to being x plus 1 squared minus 1. And then hit graph. Okay, and again, what you'll see is now we're a little bit left and now we're a little bit downwards as well. So if I predict where my vertex actually is here, well, again, it'll be those numbers in the bracket and the constant, really. But now if I rewrite this equation, it's the same thing as saying x minus negative 1 squared minus 1. The generic format of this formula has a minus sign in it. In order for us to have a plus sign, I must have put in a negative. So my vertex is actually at negative 1 as a value for x, negative 1 as a value for y. And again, you can see that the graph has changed slightly. Right? It's moved, it's translated left and down. Sometimes it could be downwards, sometimes it could be right, could also be upwards as well. It really depends on what the equation looks like. So we can graph all of these in here as well. You can try them out and see if you can graph it on there, and I'll have the completed ones in that solution for you. But if we're going to explain how the base function of y equals x squared is related to this formula, well, we saw all of the other pieces and what they did to this as well. So if I think about this, h, that number, okay, so this controls left and right movement, and k controls upwards and downwards motions. Okay, so let's say controls up and down movement. Right? It was that constant that controlled our y-intercept. It was the number attached to x that moved things left or right. And if I had two numbers in there, I had both a h value and a k value, well, now I can start to move diagonally because I can go left and right, but I can also go up and down at the same time. So if you think about, what this form can really do for us, well, this is what we call vertex form. And really, h and k are the coordinates of said vertex. So I'm going to know where that vertex happens to be based on those coordinates. You can still have a line of symmetry, and we said it's always going to be the x value of your vertex, which in this case is h. So if I know the vertex, I know that symmetry line. The other thing is still true as well. If a is positive, it opens upwards. If it's negative, it opens downwards. Okay, so we're going to try and determine all of these things just based on the equation, and then we'll draw the picture underneath. So if I look for the vertex here, again, it's those numbers that are represented by h and k, right? H and k. So I know my vertex happens when h is 3 and k is 4. And compare this to the generic one, right? Y equals a x minus h squared plus k. So I know that if there's a minus sign there, I just take the number as is. But if there's a plus sign instead, we're going to reverse the sign. Okay, here I know the direction of opening as well is actually a positive because I can see that this is a positive 2 in the front. So if it's a positive, I know we're going to open upwards. If I'm looking for my axis of symmetry, well, it's the x value of my vertex, just like it was before. So x is equal to 3. Now if I try to think about the domain here, that still hasn't changed, so it's still x can be any real number. But the range, however, is different because I know that I have a vertex. And if this opens upwards, really what that means for us is we have a minimum. So I'll add that in here too. Right? If it opens up, I have a minimum and it looks like a smiley face, kind of like what you see on the calculator here. So I know that the minimum value comes from the vertex as well. So y has to be greater than or equal to that minimum value of 4. Okay, so all the same information, and really that 2 in the front just basically controls how narrow or wide this is. So if I just graph this, and really we're just trying to sketch it to see the shape. It doesn't have to be perfect, but it will give us a rough estimate on what it looks like. So we'll put the vertex on here at 3, 4, right, somewhere here. Now if it opens upwards, you're not going to have any x-intercepts. So in the last format I had, right in our last lesson, I couldn't actually have graphed this by hand because I would have had to factor it to do it. And if there's no place where it crosses the x-axis, well, I'm not going to have any factors, so I really couldn't have drawn it. And if this opens upwards, right, you're symmetrical around 3, and your graph looks something like this. Like, it's not exact, right? It's not perfect, but it really doesn't need to be. It's just a sketch to see the shape. And you can graph it to double check, so we'll clear all those out. We'll go 2x minus 3, then square it, plus 4. And then hit graph. Somewhere up here, ideally, there it is, exactly where we expected it to be. You know, I got the basic shape of it down. I know where the vertex is. That really is all we need here. You can try the same thing for B as well. Determine the vertex first. And again, this is one of the ones where you see a plus sign. So really, what we put into this equation, this is the same thing as saying negative 1/2 x minus negative 6 squared minus 1. And the only reason I did this is so I can see the actual number here is actually minus 6. So I know the x coordinate is negative 6, the y coordinate is the constant negative 1. Direction of opening comes from the sign in the front. This one opens down this time because it's a negative. Axis of symmetry, always from the x coordinate of your vertex, so x is equal to minus 6. Domain again is still any real number. Range always comes from the vertex. Now if this opens downwards, it means we have a maximum. So there is one number where I can't be bigger than, and I know it comes from the y value of my vertex, so everything has to be less than or equal to negative 1. And again, graph it to check. Negative, I'll put it in brackets, sorry. So negative 1/2. And then we've got an x plus 6, that's squared, and then a minus 1 graph. You know, I didn't draw the picture here first, and I know it's not right because I forgot a square. So let's insert the square here. So I'll leave my equation there. Now it should be right. Actually, my brackets are in the wrong spots. Let me take this whole thing out. Try this one more time. So negative 1/2 x plus 6 squared minus 1. So before I hit graph, let's actually draw this. So at negative 6, negative 1, there's my vertex. Okay, opens downwards, so it'll look something like this. Graph. So somewhere in that, there we go. Right where we expected it to be, you know, got the basic shape of it. Really, that's all we need. It doesn't have to be exact. We're only looking for a sketch here. Okay, not something super specific. So I know generally where things are going to be, and that's really all I need. Okay, now same sort of thing with this format as well. If we're just given a graph, I can actually determine this format as well based on what I'm given. So if I'm given something and I'm really just given a picture here, and I want to make my equation in that format, well, I need a couple things. I need to know what the vertex is, and then I just need to know another point, right? It really doesn't matter which point that I use as long as it's something you can clearly see on the graph. Okay, try not to use an x-intercept because A, it might not line up perfectly, and plugging it into your equation is going to give you 0. So use any other point. The y-intercept is a good one. And then we can solve for that missing value again for A. So we'll do the same thing like we did before in the sense that, well, I just want to make an equation here, but we're going to use our new format. Right? So x minus h squared plus k. Previously we did it using the other one with the x-intercepts, but this one is built using the vertex. So I need the vertex first. I'll put it in pink here. So the x coordinate's minus 2, y coordinate of 6. There's my vertex. And I just need some other point for x and y. Okay, so I'll use the y-intercept here to do it. 0 is x, minus 6 is y. So I'll plug those 2 points in. because I know 4 out of the 5 variables now, and really this is going to be x and y. My other one is going to be h and k. The only one I don't have is a. Okay, so let's plug them all in. So y is going to be minus 6, and I'll try to keep it color-coded, so I'll write a little bit slow here. And then x we said was 0, so that should be pink. And minus h, so we'll subtract. The value for h is minus 2, so again you can really see that double negative showing up. This is why we did what we did before. And k is going to be, oh, I didn't even color code it, like I said I would. Minus 2, there we go, and plus k, so plus 6 on the end. Okay, so the only number that we're missing is a, which is what we're going to find. So if you go to simplify here, let's do the brackets first. So minus 6 is equal to a. That ends up being, well, positive 2 squared is 4, and the plus 6 on the end. So if you subtract a 6 on both sides to simplify, you're going to end with minus 12 is going to be equal to 4a. Divide both sides by 4 for our last simplification step. So I know that the value of a here is minus 3. So that's what's telling me that this is going to open downwards because that value for a is a negative. So therefore I now know my equation is y is equal to negative 3 x. Use your vertex to make this, so x plus 2 squared plus 6. Okay, there's my equation. You could graph it in your calculator to find that vertex and y-intercept like we did last time, but they'll end up being the same number. Okay, we can try the same thing out for b as well. So again, find the vertex first, which there it is. So it has coordinates of 5, negative 4. Y-intercept again is 0, positive 6. So I know I have an x and a y value. I also know I have a h and a k value. The only thing I can't read from the graph is a. So I gotta solve for it. So same formula. Y equals to a, x minus h squared plus k. And again, h and k tell you your vertex coordinates. X and y are just some other point. So plug everything in. So 6 is going to equal a, x is 0, minus h squared minus 4. Okay, so I've got everything where it's supposed to be, and then we're just going to simplify to get our final answer for a. So 6 is equal to a. That works out to be negative 5 squared. A minus 4 is still there, so we'll simplify that set of brackets for 25a minus 4. Add 4 to both sides to create some 0 pairs and simplify. Your 4's will disappear because you've made those 0 pairs. They simplify and go away. So 10 is equal to 25a. And if you divide both sides by 25 to simplify, well, you do end up with a fraction that we can actually reduce into lowest terms by dividing both the top and the bottom by 5. So you end up with 2 over 5 as your value for a. Okay, so now I know that it's a fraction, which is totally fine. It could happen. So y is going to equal 2 over 5, x minus my x coordinate of my vertex, so x minus 5, and then minus 4 on the end this time, because my y coordinate of my vertex was a negative. The one thing I didn't tell you here is in this format, that constant is not the y-intercept. Right, and it's very easy to see that because, well, I know my y-intercept is 6. The constant here is minus 4. So in this format only, the constant is actually the y value of your vertex, not your y-intercept. But really, this is the same process as what we did in the previous video. We're just using a different form of an equation to do it. Right, these two absolutely can be factored, but what you'll notice is those x-intercepts, if you try to use them, they don't line up perfectly. Right, so if my graph doesn't line up perfectly on the x-intercepts, well, I can't really use this format that I'm currently writing because I can't confidently say what the intercepts of R and S happen to be. Right, I can't use it. I do, however, know that the vertex lines up perfectly, which is why I've chosen to use this method. Okay, This third example here will give us an idea of whether or not I can even make an equation based on what I know. So what I'm asked to do is determine the number of intercepts for each, sketch the graph. Well, if I know where the vertex is, and I know which direction this opens, I'm going to be able to figure out if it will have any x-intercepts or not. So for A, think about where the vertex is going to be. Right? Look at that form of this equation, and I know h is going to be 2, and k is actually -5. So +2, -5, make a best estimate somewhere down there. I do know it opens upwards. So there's what it could look like if I graph this. So I know that there are 2 x-intercepts. Right? That's something that I absolutely know. I don't know what they are. Right? I don't know if they're perfectly where I've drawn them, but I do know that there are 2 of them. For B, think about where that vertex is this time. Well, I only have a number for h, so really if I add 0 as a constant, well, now I have k. I could add 0 to something and not change it. So I know that my vertex here is on an x-coordinate of 1, but a y-coordinate of 0. And again, this is going to open upwards. And this one also has, well, really it has 2 x-intercepts, but it looks like it only has 1. Because I can rewrite this equation, so the function of x is equal to 2x minus 1 multiplied by x minus 1. So technically, there are 2 x-intercepts. They just happen to be the same number. Okay, and they happen at this exact same place, which is why I can write this as, x minus 1 squared. So we would say that they have 2 equal x-intercepts. They just happen to be the same. So still, this is technically 2 intercepts. If you think about C, well, again, we just need the vertex. So x-coordinate this time is actually -2, because I can write this as -2 squared. Right, that double negative in there is what tells me that the sign is different. So here I'm going 2 left, 1 down. So there's my vertex, and I actually open downwards this time. So here I also know that there are no x-intercepts, which is entirely possible, right? It is something that can happen. Clearly, there's the graph of it, right? So I'm going to be able to tell just by drawing a little picture. Now, if there are 2 intercepts, well, there's a good chance it can be factored. If there are no intercepts, well, it can't be factored at all, because it will never cross. Okay, so without even trying to solve anything, I can really determine how many intercepts there are going to be just by taking a look. Now, you can do this on your calculator as well. As long as I have a graph, I can determine where there's going to be. So I suppose for our course here, right, for our purposes, let's just say that there's 1 x-intercept if it touches twice, because it's the same value, right? There's really no point in me writing the x-intercept of 1 multiple times, because it's the same number. So we'll keep it simple and not get into all the technicalities of like, well, if it's the same, it happens twice, all that sort of business. So these would be our 3 cases, right? Either there's 2 x-intercepts, it crosses twice, it touches it once, so I'm going to see only 1 x-intercept, but this is where I need to remember that it could look something like this, right? The format of it, when there's 1 x-intercept, you're only going to see 1 factor in there, but you're going to see it 2 times. Okay, so that's the special one to think about. Now, if there are no x-intercepts, well, it's never going to touch the x-axis. Could be above it and opens upwards, could be below it and it opens downwards, but it won't cross. Okay, so really those are the 3 cases. Now, to actually go find it, if you're given a y value, there's really 2 things we can do here. One of the things which we didn't really talk about before is to calculate, a 0. Right? What we talked about before is taking each of the factors, we made them equal to 0, and we solved that little tiny equation. So if I graph one here, x squared plus 5x plus 6, right? And I'll zoom in closer to that vertex there. Okay, what you'll see is it does cross twice. right? Really, really close to it. And if I hit second trace, the second option on there says 0. Okay, and what your calculator will ask you is the same questions it asks you for the vertex. So just make sure your cursor happens to be on the left side of one of the x-intercepts. Okay, so this will allow you to find an x-intercept. So put it on the left side of the x-intercept. You're going to see that triangle show up on the left side of it. But then we'll say right bound. And this is where students get real confused where to put that cursor, because I'm not going to put it on the x on the right side of the entire graph. Like, I don't want to go all the way over. I just want to make sure it's on the right side of that intercept, so that when I hit enter, my two triangles are on opposite sides of one of the x-intercepts. So I can hit enter again, and it will tell me one of them, right? If x is -3, that'll make this equal to 0. Well, that's essentially what we solved for before by factoring. And I could do it again on the other one. And I'm going to find out the other value of it happens to be -2. So I can scroll over again, enter, scroll over to the right side of that intercept, enter again, and then it will still say guess like it did for the vertex, and that's where you'll see the other one of -2. So you can find it every time using, second trace and then the 0. That will do it. The instructions that you see on here are something, well, if you actually have a y value, you could find the x value that should go with it, but sometimes you may get multiple x values, which is okay. It's totally fine. We just need to be able to interpret that. So if I had this equation here, and I said there was a place where that's maybe the y equaled 1, you can see a horizontal line get drawn through it. But we just want to find the places of x where that happens. So if I follow the instructions on here, I can go second trace. Option number 5 says intersect, and my calculator is going to really ask me 3 questions again, and it will say first curve, second curve, guess. And up at the top you can see your different curves here, different lines. So there's my equation in y1, so I'm just going to press enter, and then it will automatically change to y2. It'll pick the other line, and the question will change to second curve. So I'll hit enter again, and what my calculator is going to do now when I hit guess, it's going to take those 2 lines. As long as my cursor is close to where they're going to cross, it'll tell me where they cross. Okay, so it will tell me on both of those lines where y is equal to 1, the value of x that I need is -3.6. And if I do that for the other side, I could do it one more time, but I just have to make sure the cursor is closer to the other one. Doesn't really matter how close you get, but as long as you're close enough to it and hit enter, 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 your calculator will default to telling you the other one. So it'll find me the 2 places where it crosses if I knew what that y value was. And the reason why I'm telling you this is, well, because some of those application type questions, this is really important. So think about this one where it says a soccer ball is kicked from the ground. After 2 seconds, the ball reaches its maximum height of 20 meters, lands on the ground at 4 seconds. We're asked to determine the function in that vertex form, which is the one we saw in this video, the new one. So y equals a x minus h squared plus k. That models the height of this kick. So I don't really have a graph. I don't really have a lot of information, just a couple points. Now, if this is talking about time, I know my initial point here has to be, well, the time of 0. And if the ball's on the ground, well, I have a point here. So when time is 0, height is 0. So that's my first point, the origin, right? 0, 0. Now after 2 seconds, so let's make, about halfway be representing 2 seconds. 4 seconds is the whole scenario. We can use the whole scale here. So 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay, we're equally split. So after 2 seconds, the ball reaches its maximum height of 20. So let's say the top of the grid here is 20 meters. So I know that there is the peak of this, right? When x is 2, y is 20. So I've got another point on this. And then I'm also told it lands on the ground at 4 seconds. So I know that when the time is 4 seconds, the height comes back to 0. So really, the path of this ball can be modeled by this graph. this is really what it looks like. So somebody kicked it 20 meters into the air from the ground, and then it came back down on the other side. So I really didn't have an equation. We made this just by interpreting the numbers. Now what I'm asked to do is determine the function in vertex form that models this. And it's the same thing that we did before. As long as I have a vertex, which I do, right? I've got h and k, and I have the y-intercept or some other point, well, I've got a y-intercept of, well, 0, 0. So I know x and y. The only thing I don't know here is a. So we're going to find it just like we did before. So plug everything in. So y is going to be 0 from our origin, a is unknown, x is 0 from the origin as well, minus 2 from our vertex, and then plus 20 also from our vertex. So 0 equals 4a plus 20. And if I rearrange that, I'm going to move my positive 20 to the other side of the equal sign. So minus 20 is going to equal to 4a. And if you divide both sides by 4, then negative 5 is the value for a. So in terms of that vertex form, I know what my quadratic function is now because I found that a value. Right? So therefore, y equals minus 5, x minus 2 squared plus 20. Right? And I know that's what my equation is going to be based on what I found before. And I know it's negative because it opens downward, so that's really good that we found out that it was a negative, because those things have to match. Determine the domain and range. Well, think about this in terms of this situation. X represents time, so here it can't be any values. It actually has to be only between 0 and 4, because that's really what our graph goes up to. So 0 should be the smallest, 4 is the biggest. Other than that, it can be any numbers in between 0 and 4. In terms of the height then, well, 0 is the smallest height, 20 is the biggest height, but any real number in between. Because so you can literally imagine, here's my terrible soccer ball, looks more like a football, but anyways, you can imagine it being kicked, and over time it goes up to the top and then starts to come back down on the other side of things. But it can't go through the floor. Once it hits the ground, it stops. So I can only go up to a maximum height of 20, minimum height of 0. My time happens from 0 to 4. Right? So there's essentially the situation here. Okay, what was the height of the ball at 1 second? Well, I don't really know, but I could, make a best estimate right about halfway in between, 0 and 2 should be 1. So if I just, take a look upwards and go over, like I could get an approximation from this, but now that I actually have an equation, I can graph it in my calculator and get an exact value. So negative 5 brackets x minus 2 squared plus 20, and then hit graph. And you probably won't see anything based on the scale. We gotta adjust this. So the minimum value for x, I want it to be 0. I want it to match my picture. Maximum, I want it to be 4. The x scale is 1s. Y minimum, the lowest y was 0, we said. The biggest y we said was 20, so I'm just going to make it 25, just so I can see enough room. Okay, so there's the same picture. Now, if the height of the ball at 1 second, well, there's two ways I can do this. Right? I could put y as, since y is height, if I make y 1 in my equation, I could solve for it, but then it becomes a problem of square rooting. So let's just graph this, right? If I know that y is supposed to be 1, I could make a second equation where y is 1, and there's the line that I'm really looking for. Now my scale is a little bit different here in terms of, heights and how I split things up here. But if there's y is equal to 1, that's 1 second. Oh, hang on a sec. That's why it didn't work the way I wanted. Because I don't know. Height of the, oh, that's because this is time. That's why. That's why it looks weird to me. Sorry, let me delete that. And if it's the height of the ball at 1 second, I was thinking about this backwards. So that 1 second is actually x, right? That's time. So I could put 1 into the equation and solve it. But if I do second trace in the calculator, Option 1 lets me input a value, so I want x to be equal to 1. So when I hit enter, when x is 1, it will tell me the height that should match with it. So if I put 1 into this blue equation and solved it, well, that's why, yeah, now it makes sense. Then y is supposed to be 15. Right? The height of the ball after 1 second is 15 meters, which makes sense. Part D is what I actually wanted to do. And at what times to the nearest tenth does the ball reach a height of 12 meters? Okay, so this is where I'm going to need that other thing that I was talking about on my calculator. So if the height at 1 second was 15, right, that's what we just found. So that's 15 meters, roughly, like my graph's not perfect. So a height of 12 meters should be less than that slightly. So there are 2 places where I have a height of 12 meters, right? Which is why it's worded and it says what times, plural. And I could find that in my calculator by hitting y equals and I'm putting in the height of 12, right, for another line. That's where it comes in. So now I can actually go to graph this. So second trace, option number 5 is intersect, and move your cursor close to one of those intersection points and then hit enter 3 times. And what your calculator will do is tell you the time it takes to get to a height of 12 seconds. So 1 time to the nearest tenth happens at 0.74 seconds. But remember, whatever goes up has to come back down, so it will reach the same height again, just later in time. So I have to do this one more time. Move that cursor over to the other side of this graph. And that should be close enough. Enter, enter, enter. And there we go. There's the other one. So it either happens at 3.3. Okay, so it either happens at 3.3 seconds as the ball is coming down in its trajectory, or it happens at 0.74 as it's going up, right? So it hits the same height multiple times, which is fine, right? Physically, that makes sense. Okay, so we saw our third form of our quadratic equations and what it actually allows us to do in terms of the information that we're given. And again, you've got a nice summary on the bottom that gives you everything, and you'll have a bunch of practice ones also where you can try out all of the same skills we talked about. So if you need to see anything again, I mean, go back, obviously rewatch part of it to try it out, and then when we do the next one, we'll talk about how to solve them by graphing. So we'll revisit all of this graphing stuff again in the next video. It will be a dedicated video on all the graphing pieces. So anything that I did here we'll put together in the other one so you can have it all in one place. So I hope that was helpful. You'll find all the links up above as well. So look out for that next video up in the top corner. You can click right on it. And until then, we'll see you next time.